Welcome back. In our last video, we looked at the concept of the line integral and we also stated the Green's theorem. In this video, we would prove the Green's theorem as rigorously as we can, and we have already put in some groundwork for that. First, the theorem. Let C be a simple closed curve bounding a region R, and let ax, ay, and their first partial derivatives be continuous in the region R. Then, the integral over C of ax dx plus ay dy is equal to the double integral over the region R, del x ax minus del y ax, del x ay minus del y ax dx dy. Now, we have tried to make representation of what this region is using this diagram. I have made it as explicit as I can. Of course, C being the simple closed curve just simply refers to this curved line here. Now, of course, when you say a simple closed curve, you are simply talking about a line that you start from a point and then you draw and end at that same point, right, without any breakages. So now, of course, the region in the middle, that's your R, and then you have your ax, ay as your functions within, or that are determined within that region and continuous within the region. So let us solve this. Now, in order to prove the Green's theorem, it suffices for us to evaluate on the real axis, for the real axis along AEB and then AFB, right? That will complete the entire curve. And then for the imaginary axis, which is the y-axis in this case, we can evaluate along EAF and EBF, right? So why is it important to consider these two axes? Because remember, the Green's theorem converts the integral along the entire curve, the simple closed curve, into a double integral along the region based off the real and imaginary axis. So we are going to follow that same process for this proof as well. And the goal is to show that when we evaluate across these two axes, we are going to have the full region, which is the integral over C. So let us see exactly how this is. We'll start first and foremost along the real axis so that we can have clarity. So, so let's start. For the real axis, of course, to evaluate the goal, we are to show, right? We are to show that integral over C ax dx plus ay dy equals the double integral over R of del x, which is the partial derivative of ay with respect to x, minus the partial derivative of ax with respect to y dx to y. So now let's start. So first off, we'll take for the real axis, right? So for the real axis, we will be evaluating along AEB, that's this down part, and then AFB, that's the upper part. Now let's see what happens in that case. Along AEB, right, for the real axis, we will notice that the first value of x, which we have, of course, x1 would be A, and then the second value of x we have, x2, is B, which are these two values here on the real line. Now, these are the fixed values because we're evaluating on the real axis, whereas the y values are variable values, right? And then y2 is equal to capital Y2 of x, which means that these values of y flow within the real axis. Hence the reason why this curve is completed in the first place. So while we know the start and end points of the x, the values of the y, right, changes within that curve. Now, let's put that all into perspective. We'll consider the right-hand side. So if we consider the right-hand side, we'll have that the double integral over R of del x ay minus del del y ax dx to y can now be rewritten separately. So first we can break the integral into the integral over r del del x ay dx to y as the first part minus double integral over r del del y ax dx to y. Now we have this break in transmission. So let us see what exactly happens within this concept. Now, if we take the first part, which is the integral over r, now, based off each of these values in the right-hand side that we have here, we will notice that each of these values, of course, will equal to one of those values in the left-hand side. Now, on the real axis, which is along AEB and AFB, we'll be considering the double integral over r of the partial derivative of ax with respect to y dx to y. Now, we can, of course, rewrite this as a double integral of r del del y ax to y dx. So that if we now expand it based off the coordinates we have on the real axis, we will now have that we can split this integral into the integral of x equal to a to b, and then into the integral on the y part, which would be in this case y equal to y1 of x, and then y2 of x, del del y ax to y, and then outwards dx. Now, the reason why we are doing this is very simple. Is because on the real axis, right, which is on this point where we have AEB and then we have AFB as we have it, you would notice that what is bringing the most of the contribution here is the horizontal sides. So the horizontal sides are contributing more, which is where the y values exist. On the verticals, since you have fixed values of x, it means on the verticals dx is 0 on that point. Hence why we integrate inside with y first and foremost. And of course, this balances out the partial derivative here, which is simple. Now, when we integrate this by law of integrals, we'll have this to integrate from a to b, which is of course x, and then the inside function will be ax of x comma y evaluated from y1 of x to y2 of x, of course, still multiplied by dx outward. So that by the time this is expanded, remember, we put in the upper bound and then subtract by the value on the lower bound. So we'll have this as the integral from a to b of ax xy2 minus ax xy1 dx. Now, this is very, very interesting. By properties of integrals, of course, we can break this integral into two if necessary. We can break that to see the integrals itself, but then you could just simply look at this integral which you have and apply your fundamental theorem of calculus to it. And what does that say? It says when you have an integral from a to b, right, such that the functions inside stretches from the same function but different values of y, which of course start from the upper bound to the lower bound, then essentially you are still covering the entirety of the direction for that integral. Now, if we break this, this becomes a little bit clearer to see. Now, what exactly do I mean? I mean, if you decide to break this integral, you could have it as an integral from a to b of ax xy2 minus the integral from a to b ax x y1. Of course, this is dx, this is also dx in this case, such that if you rewrite this as a negative value, I could write it as the integral of the minus integral from b to a ax xy2 dx minus the integral from a to b ax xy1 dx. And this is what I have. Now, based off this, by the time I factorize the minus 1 out, we will notice that this becomes, so we have the integral over r of del y ax dx dy will be equal to minus into the integral from b to a ax xy2 dx plus the integral from a to b ax xy1 dx. Now this is interesting. Why this is interesting is because if you look at this integral that you have, you would notice for a fact that for this integral, you are starting from a to b over the inner bound of y and then going from b to a over the upper bound of y, which will mean that you are moving from the start point to the end point and then from the end point back to that same start point. So it means you are completing the entirety of your circle, right? The downward region and then from the downward region back to the start. So essentially you are going AEB and then back to the start point. So you are completing the entirety of the motion. So this would mean that here this integral would break down by fundamental theorem of calculus back to the integral over c, which is ax dx. So you have that the integral of r del y ax dx dy is going to be the same thing as minus integral over c ax dx. And this gives us our first part. Do not forget that this is our entirety of the integral, which we want to consider, right? And this is, of course, the left-hand side. So we have picked one of it, which is this one, right? Of course, we'll now pick the second one on the imaginary axis. Now, of course, this should definitely mean that we are saying that minus the double integral of r del y ax dx dy is going to be the integral over c ax dx. So that, of course, solves that. Now, when we move to the other part, this time around for the imaginary axis, which in this case we'll be evaluating along EAF and EBF. So when we say EAF and EBF, you know we mean EAF and then EBF. So you see in this case, the vertical sides are the ones that exist. And if you consider on the horizontal, the y will be equal to 0. So let's bring out all our values. In this case, we would have that y1 will be equal to e, that's the lower bound, and then y2 will be equal to f, that's the upper bound. And then on the x-axis, on the x points, x1 will be equal to x1 of y, and then x2 will be equal to x2 of y. Here we go. Now, in this case, we'll be taking the double integral of del x ay dx to y, which happens to be the second integral. Right? It happens to be the second integral. Now, if we take this, what would happen? We would be integrating on the outward y equal to e to f, and then on the inward we have the integral x equal to x1 of y to x2 of y of del x ay dx dy. This is what we are going to have, of course, in this case. Now, this, of course, breaks down. If you apply the integral over x first, you'd have the integral from e to f of ay x, y, x1 of y, x2 of y, dy. So that by the time we evaluate, we would have the integral from e to f, ay x2y minus ay x1y dy. And then, of course, same process. If we break this down, we have this to be e to f ay x2y to y minus integral e to f ay x1y dy. And then at this point, of course, if we change our integral by property of integrations or for property of integrals, this can remain integral ay x2y to y plus integral f to e ay x1y to y. So we see that the full motion has been completed yet again from f to e and then e back to f, right, as the case is. So we've completed the motion. So this reduces yet again to the integral over c of ay to y. And of course, this is the double integral over r del x ay dx dy. So this is what we have. So if we put it all together on the right hand side, it means that we will have that the integral over r dx del x ay minus del y ax dx dy, which of course we have here to be equal to this, which breaks down into that, is now going to be equal to the first part of this, which is the double integral del x ay dx dy, which is what we have here, has given us the integral over c ay dy, and then the minus part has given us the second one, which is the integral over c ax dx. So if we bring it all together, you'll see that we would have, of course, our left-hand side, which is the same thing as the integral over c ax dx plus ay to y as our final result. So this is our left-hand side. Hence proved. So what we have seen or what we have noticed here is that first and foremost in solving the proof of the Green's theorem, the very first thing is to understand the flow of movement on the vertical sides as well as on the horizontal sides. On the vertical sides, which is where the imaginary axis will be, would evaluate along the verticals such that the y values would be fixed and then the x values will be variable. On the horizontal side, which is where the real axis would be, would evaluate such that the x values will be fixed and then the y values will be variable. Doing this on both sides would allow us to get the integral over the simple closed curve C as the case is. I hope this has been very, very clear and you've been able to follow through with it from the start, which is from where we took the real axis and we expanded based off the real axis, and then when we went into the imaginary axis and then expanded based off that as well. As always, make sure to like, share, and subscribe, and turn on your notifications if so that you do not miss any of our videos. And if you have any comments, you can always share with us in our comment box.